Energy diagrams give us an easy way to view how energy is changing over the course of a reaction. So let's take everything we've learned from the text so far and apply it to this generic energy diagram that I've written here. We'll start by identifying the reactants and the products. On the left we will have the reactants over here, I'll just put an R, and then we'll have our products, and in this case we have two different products based on where they landed on the energy scale. Since we're looking at change in free energy, we can define both of these products as being endergonic or exergonic. Looking at the white pathway that led us to this product, and we'll consider that reaction 1, we ended up getting a product that was lower in energy compared to the reactants. Since we have that negative change, or delta G, that would be exergonic. And I'll finish writing that here. Now when we look at the other product over here compared to the reactants, we see that we actually go up in energy, so that would be endergonic. I'll write that here. So exergonic is actually going to be spontaneous since we have a negative delta G, while endergonic is not going to be spontaneous. We can also quickly identify the transition states and the intermediates of these reactions. We'll go ahead and start with the intermediates, and I'll just draw a small I where we find those. And the easiest way to find the intermediates is to look for the valleys in the reaction. So they have a valley here. I'll just put 1 since they're essentially the same, and I attempted to draw them that way. We have another here and another one here. And once again, with both of these, I attempted to make it that the white overlapped the yellowish color, reaction number 2. Now for the transition states, I'll just draw a small t. Those are the peaks. And remember that transition state describes this high energy time in the reaction in which bonds are being broken and formed. Now on the very right over here, I'm going to draw 2 t's because I attempted to show that these transition states were actually different from each other. Also remember that intermediates are molecules that you're actually going to see happen over the course of your reactions. Typically a good example is carbocations that you form as you're doing a mechanism. Now I want to draw your attention to this part of the reaction diagram. As I mentioned before, I wanted to show here that both these transition states were different, whereas the rest of the reaction diagram I attempted to make the same, but I couldn't get the exact overlap. Notice how the reaction that had the higher peak right here led to some products that were actually lower in energy compared to the reactants. And like I said, we'll call that reaction number 1, or pathway number 1. And as for the other one, we'll call that pathway number 2. Since the first pathway led to products that were the lowest in energy or the most stable, we call those the thermodynamic product. Now let's look at the difference between these two peaks, as I've drawn your attention to earlier, the transition states. For pathway number 2, we actually had a lower peak, which means that the activation energy is lower. It's easier to get over the hill. Since the activation energy level is lower, we call this the kinetic product, because it depends on the rate of the reaction. And once again, it's trying to walk yourself up a slide, and if we compare between reaction 1 and 2, with reaction 2 it's easier to get over the hill of energy. Before we wrap up with the next slide, I wanted to bring up the Hammond postulate, which states that the closer 2 points on an energy diagram are in relation to each other, the more structurally similar they will be. So I'll propose a thought question. With reaction number 1, are the products or the reactants more similar to the transition state right here? In the previous slide, we started by looking at a reaction diagram that was already drawn. But we can actually draw an energy diagram based on a given reaction and what we know about that reaction. And it's not too hard. Let's just say that we're starting with our reactants right here. And the point, essentially where you start, how high, is pretty much arbitrary as long as you put the valleys or the intermediates correct relatively. since we're going from this alkene to this carbocation, we would expect that the intermediate, or this carbocation, would be higher in energy compared to the product. So when I draw the energy diagram, I'm going to go up in energy, have my transition state, and let's say we'll go there. Once again, these levels or change in levels are arbitrary, but the idea is that we want to make sure that we have this increase in energy from the reactants. Now going from the intermediate, the carbocation, to this, we're going to have another transition state, and in this case with this addition reaction, the products are going to be lower in energy compared to the reactants. So we'll want to make sure that going from a level that we actually go down in this case. We have our products and our reactants. Now we can go back and essentially link the parts of the reaction shown above to areas on the reaction diagram. So if I just do arrows, we know that our reactants are here, our intermediate was here, and our end product was right here. Now something that might seem confusing is, okay, what do we do about the transition states that we have here? Does one need to be higher than the other? With a lot of the problems you'll be working with in the textbook and in the class, the position of transition states in relation to each other isn't that important. Like I said, the real important thing is to make sure that your values, or where you're placing your intermediates, are in relation to the reactants, products, and other intermediates is important.